Welcome back to the deep dive. There's a specific kind of cognitive dissonance that happens when we talk about AI risk. If I say those words to a person on the street, or even to some tech journalists, the image that pops into their head is, well, it's cinematic. It's dramatic.
It's the red eye of HAL 9000.
Right. It's a superintelligence deciding that humanity is a resource allocation error that needs to be, corrected.
It's the Hollywood baseline. We're conditioned to view AI risk as an existential battle for survival. It creates a great blockbuster, doesn't it?
It does.
But it's not exactly helpful for the person trying to actually deploy a machine learning model in a bank or a hospital next week.
Exactly. The reality of managing AI risk is surprisingly granular. It's practical. It's sometimes frustratingly detailed.
Yeah.
And as we're going to find out today, it's sometimes incredibly physical.
Physical, yeah.
We are talking about everything from the logic of the code down to the literal atoms in the hardware. It's not about rogue robots. It's about dust. It's about bad wiring. It's about a human operator getting bored and checking their phone.
It is surprisingly mundane, and yet that mundanity makes it infinitely more complex to manage. We aren't fighting Skynet. We are fighting entropy. We are fighting complexity.
And that is why I'm genuinely excited about the document we are breaking down today. We are looking at a document that is effectively the antidote to that sci-fi hype.
Like that frame.
We are diving into BS, EN, ISO IEC 23894.2024. Specifically, this is the guidance on risk management for artificial intelligence.
Okay.
And before anyone tunes out because they heard the word ISO standard, let's be clear about what this represents. This isn't a blog post. This isn't a think piece. This is the heavy artillery of compliance and safety.
That's a crucial distinction. When an ISO standard gets published, especially one with this specific designation, BS, EN, ISO, IEC, it means the heavy hitters have agreed.
Right.
This is the European standard. It's the international standard. This is the playbook that regulators and auditors are going to be using to judge whether an organization has actually done its homework or if they're just, winging it.
It's about integrating AI risk management into the organization's overall flow.
That's the goal.
And the scope of this document is massive. It covers the whole life cycle. But for today's deep dive, we aren't reading the whole phone book. We are zooming in on a specific fascinating section, Annex B.
Annex B, the risk sources.
It sounds innocuous, doesn't it? Risk sources. But as I was reading through this, it struck me as essentially a catalog of failure modes. The list of where the trouble starts.
I like to think of it as a map of the minefield. Most risk management focuses on the explosion, the bad outcome. We lost money or the car crashed.
Right, the effect.
Exactly, the effect. Annex B asks a different question. What was the spark? Was it the code? Was it the data? Was it the hardware? Or is it just the fact that the world is too complicated for the math? If you want to manage risk, you can't just look at the explosion. You have to look at the wiring, the fuel, and the match.
So consider us your instructors for this session. Our mission is to walk through sections B.1 through B.8 in order just as they appear in the standard.
A guided tour.
We are going to unpack the list of places where AI risks come from. And I think what's going to surprise people is how physical this gets. We're going to talk about logic, sure, but we're also going to talk about outer space.
We are indeed. It covers the full spectrum from philosophy to physics.
Let's start at the beginning, B1 General. This sets the stage. Now, usually the general section of a standard is just, preamble fluff.
Right, throat clearing.
But there's a very specific assertion made here that dictates how you read the rest of the document.
It's the no one-size-fits-all clause. It sounds obvious, but in compliance, people love checklists. They want to take Annex B, photocopy it, tick the boxes, and say, okay, we're safe.
Of course.
Section B.1 explicitly forbids that mindset. The standard starts by making a crucial point. Identifying risk sources isn't a one-size-fits-all exercise. The text emphasizes that the risk sources depend heavily on the nature of the system and the application context.
Because an AI powering a video game recommendation engine is fundamentally different from an AI powering a pacemaker.
Exactly. Let's take a simple example. A generative AI that recommends cocktail recipes based on ingredients you have in your fridge.
Okay.
What are the risk sources there? Maybe it suggests a gross combination. Maybe it hallucinates a fruit that doesn't exist.
Low stakes.
Extremely low stakes. Now, take that exact same underlying architecture, a pattern-matching neural network, and apply it to a diagnostic tool for reading MRI scans to detect early-stage tumors.
Right.
The code might look similar. The math is similar. But the risk sources are completely different because the cost of a hallucination is now life or death.
A risk source that is critical for an autonomous vehicle might be completely irrelevant for a spell checker.
Precisely. The context is everything.
The source material also mentions that these risk sources need to be considered alongside the issues and opportunities described in clauses 8.2 to 8.8 of the main document. We won't go into those clauses today because we are focused on Annex B,
Yeah.
but it's a reminder that this is part of a bigger web, right?
It is. You have to read the whole map. But the takeaway from B1 is essentially read what follows, but use your brain. Apply it to your specific situation. It's an invitation to critical thinking, not just compliance.
It's an invitation to architect your own risk profile.
That's a great way to put it.
Okay, so with that disclaimer locked in, that context is king. Let's move to the first substantive category. B2, complexity of environment.
This is a big one. This strikes at the heart of why we use AI in the first place.
Right. The document states that the complexity of the environment determines the range of potential situations an AI has to handle. And it points out something kind of ironic. We often choose machine learning specifically because the environment is too complex for traditional software.
That's the core tension. If you have a simple controlled environment, like a factory floor where a robot arm picks up a specific bolt from a specific tray, you don't really need a complex neural network.
No.
You can program that with standard logic. If X, then Y. It's deterministic, it's safe. But when you move to an uncontrolled environment, like a city street...
That's the classic example. The source mentions automated driving explicitly here.
Yes. In a city street, you have pedestrians, weather, other cars, construction signs, plastic bags blowing in the wind that look like dogs. It's chaos.
It's pure chaos.
That is a high-complexity environment.
And the risk source here is what they call the identification challenge. It poses the question, can you, as the designer, sit down and list every single scenario the system will encounter?
The standard suggests it is effectively impossible. If you're designing a system for the real world, can you list every single scenario? No.
It's mathematically impossible.
It really is.
And if you can't list them, you can't guarantee your training data covers them.
Exactly. This leads to the data coverage problem. If you can't forecast all possible states, your training data will inevitably have gaps. And this creates a gap between simulation and reality.
The source talks about this gap. You can train a car in a simple, predictable, or controlled environment, like a computer simulation or a closed test track.
Sure, the lab.
But the real world is messy.
The document refers to this as the all possible states problem. In high-complexity environments, you cannot forecast all possible states, and the result of that inability is uncertainty.
And that uncertainty is the risk source.
Yes. It's not that the code is broken, it's that the system might encounter a scenario, a specific combination of lighting, geometry, and movement that it was never trained for.
The unknown unknown.
That's it. And because it wasn't trained for it, its behavior becomes unpredictable.
So the risk isn't a bug in the traditional sense. The risk is the world itself being too complicated for the model's map of the territory.
Precisely. And this is why B.2 is such a foundational risk source. You are deploying a system into a world that is fundamentally more complex than the data used to train the system. That gap is where the danger lives.
Okay, let's unpack that a bit more. When we talk about this gap, the standard mentions that this results in a level of uncertainty. How should a listener think about that uncertainty?
Think of it as a cone of possibility. In a controlled environment, the cone is narrow. You know what's going to happen. In a complex environment, the cone is massive.
It just expands outward.
Exactly. The risk is that the AI will make a confident decision about something that falls outside its known world. It might see a reflection in a puddle and think it's an obstacle, or conversely, see a white truck against a bright sky and think it's empty road.
That famous example.
The complexity of the environment hides these edge cases until it's too late.
And relying on simulation doesn't fully fix this.
It helps, but the standard warns us not to confuse the two. A simulation, by definition, is a simplified model of reality.
Right.
If your simulation doesn't include kids throwing water balloons at the car and that happens in reality, you have a risk source.
Right. So B2 is about the world being bigger than the data. Let's move to B.3. Lack of transparency and explainability. This is a topic that gets a lot of headlines.
Oh yeah, the black box.
But before we get to the scary part, the standard actually defines these terms quite carefully. It distinguishes between transparency and explainability.
It does, and for good reason. Conflating them causes a lot of confusion.
Let's break that down. What is transparency in this context?
Transparency, according to the source, is about communication. It's about appropriate activities and decisions. It's about the organization being open.
Okay.
Are they sharing their policies? Are they explaining the limitations of the system? Do they document their design choices and verification processes?
So transparency is about the process. It's about the humans and the organization being clear about what they built and how they govern it.
Exactly. It's about not hiding the ball regarding how the system was made. You can have a completely opaque algorithm, a total black box, but still be a transparent organization if you are honest about that opacity.
So you can say, we don't know how it works, but here's how we tested it.
Precisely. You say, we used this model, we tested it this way, and here are the results. That is transparency.
Explainability.
Explainability is a property of the AI system itself. It asks the question, can humans understand why the model did what it did?
And this is where we hit the black box issue.
Yes. The source highlights that deep learning models are often difficult to understand by inspection. With traditional software, I can look at the code and see, if variable x is greater than 10, do y.
But with a neural network,
it's a matrix of millions or billions of floating point numbers. We know the input, say a picture of a cat. We know the output, the label cat.
sure.
But the middle, the logic, it's distributed across all those weights. It cannot be easily expressed in human language.
It's murky.
Murky is a polite way to put it. We know it works, but we often can't prove how it works in a granular way.
And why is this a risk source? Who cares if we understand it, as long as it gets the answer right?
The stakeholders care.
Yeah.
And the risks vary based on who needs to understand.
Give me an example.
Let's take a loan application. If an AI denies your loan, you, as the user, want to know why. If the bank says, computer says no, and we don't know why, that negatively affects trustworthiness and accountability. It feels arbitrary.
That makes sense. It feels unfair.
But it goes deeper. Think about regulators. If they suspect the model is discriminating against a certain demographic, they need explainability to audit it.
Mm-hmm.
If the logic is opaque, you cannot prove fairness. You cannot prove compliance.
And what about the developers themselves?
That's a huge one. The source notes that if an organization cannot provide information relevant to stakeholders, it poses a risk to the organization regarding its own validation.
How so?
If you don't know how it works, it is much harder to fix it when it breaks, or to prove that it's working correctly in the first place. You're just poking it with a stick and hoping it gets better.
The source lists a whole parade of consequences here. It says this lack of visibility leads to risks regarding privacy, safety, security, fairness, and robustness.
It connects to everything. If you can't explain the decision, you can't guarantee you aren't leaking private data. You can't guarantee you aren't relying on a fragile correlation that will break under attack.
It's like a single point of failure.
Transparency and explainability are the lights in the room. If the lights are off, you're likely to trip over something.
That is a great analogy. So B2 was the world is complex. B.3 is the brain is opaque. Now let's look at B.4 level of automation.
This section deals with the relationship between the human and the machine. This is where the psychology comes in.
The standard describes a spectrum, right? It's not just manual versus automatic.
Right. It ranges from no automation, where the human does it all, to full automation, where the AI does everything. But the risks don't just increase linearly.
Really?
In fact, some of the spikiest risks happen in the middle.
This is the human in the loop problem.
Exactly. The standard discusses the specific risk where an external agent, usually a human, must be ready to intervene.
This is the self-driving car scenario again. The car drives itself on the highway, but if it gets confused, it beeps and tells the human to take the wheel.
That moment, the handover, is a massive risk source. The standard highlights constraints here, specifically time constraints and attention constraints.
Because if I've been letting the car drive for an hour, I'm probably checking my email or staring at the clouds. I'm not paying attention.
That is complacency. The document explicitly lists complacency as a risk. If the human gets too comfortable, they might not be ready to take over safely or securely.
It's asking the human brain to go from zero engagement to high-stakes decision-making in a split second.
And human brains are terrible at that. It takes time to reorient. Where am I? How fast am I going? Is that a truck?
That's a terrifying thought.
In that gap, that few seconds of confusion, you have a massive safety risk.
So the instructor insight here is fascinating. Partial automation can sometimes create more risk sources than full automation.
Yes, because you have the risks of the AI failing, plus the risks of the coordination between the AI and the human failing.
You've doubled your surface area for trouble.
Exactly, you have.
It's like a relay race. The baton passes where you drop it.
Exactly. If the robot runs the whole race, no baton pass. If the human runs the whole race, no baton pass. But if they have to swap halfway through safely at speed, that's where the chaos happens.
Okay, let's move to B.5 risk sources related to machine learning. The document calls this section out specifically because ML is different from traditional software.
This is a dense section. It really gets into the mechanics of how these systems are built. The headline here is Dependency on Data.
Traditional software depends on rules. ML depends on data.
Correct. The behavior of the system depends on the algorithms and the data. You cannot separate them. If the data is bad, the model is bad.
Garbage in, garbage out.
The oldest rule in computing.
The standard breaks this down into a few categories. Let's start with data quality.
Inadequate data quality affects everything. Fairness, safety, robustness. The source specifically mentions representation.
This brings us back to issues of bias, doesn't it?
It does. If your data doesn't represent the actual domain of application, if there are gaps, you get business risks. For example, if you train a facial recognition system only on young people and then try to use it in a retirement home, it will fail.
That's a representation failure. The data didn't look like the real-world context.
Precisely.
Then there's the data collection process itself.
This is often overlooked. The process of collecting data is a risk source. How did you get it? Did you have permission?
Right.
The source lists ethical and legal risks regarding sourcing and storage. If you trained your model on data you didn't have the rights to, the risk source is the provenance of that data.
And it mentioned something scary. Adversarial attacks.
Data poisoning. This is where a bad actor intentionally feeds bad data into your training set.
Okay, explain that.
Imagine someone putting invisible stickers on stop signs so that the self-driving car learns to ignore them. That is data poisoning. You aren't hacking the code, you are hacking the learning process.
That is terrifying. And then there's the issue of time. Continuous learning.
This is for systems that keep learning while they run. They ingest production data and update their model.
The source uses the term drift.
Yes. Drift is the risk that the behavior changes during use in ways that were not expected. The AI learns bad habits.
Can you give an example?
Imagine a chatbot designed to be helpful. If it learns from the conversations it has with users, and users start trolling it or being rude, the chatbot might drift and start being rude back.
So it's not programmed to be rude.
No, but the data it's consuming in the wild is changing its behavior.
So it's evolving.
And if you aren't monitoring that evolution, you have a massive risk source. The system you deployed on day 1 is not the system you have on day 100. It drifts.
The B.5 really highlights that ML is a living, breathing thing, or at least it acts like one. It eats data, it changes, it can be poisoned.
It's organic risk management versus the architectural risk management of traditional code.
Which is a perfect transition to B.6 system hardware issues. Because now we are leaving the organic world of data and crashing back into the hard, cold reality of physics.
This is one of my favorite sections because people often forget it. We think of AI as existing in the cloud like it's magic.
Right.
But the cloud is made of servers, and servers are made of silicon.
The standard lists the usual suspects, defective components.
Right. Short circuits, defective bus lines, oscillators that drift, the standard stuff that breaks any computer. But remember, AI workloads are incredibly intensive. They push hardware to the limit.
But then it gets really interesting. Soft errors.
Yes. Unwanted temporary state changes.
And the source explicitly mentions radiation.
High energy radiation. We are talking about cosmic rays.
Okay, stop. Cosmic rays, we are managing AI risk and we have to worry about space.
Absolutely. A cosmic ray is a high energy particle from space. If it hits a memory chip just right, it can flip a bit. It changes a 0 to a 1.
In a normal picture, that might just be a corrupt pixel. Who cares?
Exactly. But in a deep learning model, that bit might be part of the weights we talked about. It might be the number that tells the car, is this a pedestrian or a shadow?
Oh.
If you flip that bit, the logic of the model changes instantly and silently.
And there's no way to know it happened until it fails.
Exactly. It's a silent, invisible risk source from outer space. It's the butterfly effect, but with astrophysics.
That is wild. But B.6 also talks about risks that are a bit more terrestrial. Hardware mismatch.
This is the transfer learning problem. You train your huge AI model on a massive server farm with thousands of GPUs. It has infinite power. Then you compress it and put it on a smartphone or an edge device.
Like a smart camera.
Right. The source notes that the differences in processing power, memory, and accelerators can constrain the model. You might have to simplify the model to make it fit.
And simplifying it might make it dumber.
Or less robust. or slower. If the AI needs to react in 10 milliseconds, but the chip on the camera takes 50 milliseconds, you have a safety risk. The hardware constraint is the source of the risk.
And finally, for hardware, network dependencies.
If your AI lives in the cloud, you need the internet to reach it. Bandwidth restrictions and latency become risk sources.
If the internet cuts out, does your robot stop working? Or does it crash?
A very good question. The shared nature of network resources creates unpredictability. You can't control if everyone in the neighborhood decides to stream 4K video at the same time.
Exactly.
If your AI relies on a pipe that you don't own, you have introduced a risk source you cannot fully control.
Okay, we've done environment, transparency, automation, data, and hardware. Now let's look at the timeline. B.7, system lifecycle issues.
This section acknowledges that risk changes depending on how old the system is and what stage of life it's in.
It starts with design and development.
The risk here is failing to anticipate the context of use. Designing for the wrong environment leads to unexpected failure. This goes back to B.2.
It all connects.
It really does. If you design a tool for a lab and ship it to a jungle, it will fail.
Verification and validation.
The testing phase. The risk here is inadequate processes for releasing updated versions.
The source mentions accidental regressions.
This is the classic, I fixed one bug and created 2 more. In AI, this is very common. You retrain the model to recognize a new type of road sign, and suddenly, because of how neural networks balance weights, it forgets what a stop sign looks like.
That's a regression.
And a dangerous one.
Moving to deployment.
This is where the rubber meets the road. Inadequate configuration. Resource problems. Did you give it enough memory? Did you set up the load balancing correctly? Those are all risk sources.
And maintenance update.
This is the long tail. What happens when the developer stops supporting the AI, but people are still using it?
Liability risks.
And security risks. An unpatched AI is a vulnerable AI.
But the point in B.7 that really stood out to me was reuse.
This is a crucial point. The source calls this context mismatch.
It gives a specific example. Identifying faces in photos on a social network versus identifying criminal suspects in surveillance footage.
This is the perfect illustration. Imagine you build a facial recognition system for Facebook. The stakes are low. If it tags your aunt as your cousin, it's a funny mistake, no big deal.
Right.
Now imagine a police department buys that exact same software and uses it to identify suspects in a grainy video to make an arrest.
The stakes are life-changing.
Exactly. The accuracy requirement is completely different. The risk profile is completely different. But the software is the same.
So the risk source isn't the software. It's the reuse of the software in a context it wasn't designed for.
Precisely. The mismatch is the danger, and this happens all the time. People grab off-the-shelf AI models and apply them to high-stakes problems without realizing those models were never tested for that level of rigor.
That is a powerful takeaway. And finally, the end of the line, decommissioning.
What happens when you turn it off? The source notes 2 risks here. First, loss of information. If the AI held knowledge or patterns that weren't documented anywhere else, that knowledge is gone.
And second,
decision expertise. If you've been relying on the AI to make decisions for 5 years, your human staff might have forgotten how to make those decisions.
you've de-skilled your workforce.
You really have. And replacing a decommissioned system with a new one changes how information is processed and how decisions are made. It's a chaotic transition.
Decommissioning isn't just pulling the plug. It's a systematic change that introduces risk. All right, we're at the final section, B.8, technology readiness.
This is about maturity. How grown up is the tech?
The standard contrasts immature technologies with mature technologies.
Immature technologies are risky because they are unknown. There is little history. You are the guinea pig. You don't know what you don't know.
But mature technologies have risks too.
They do. The biggest one is complacency. Oh, we've been using this algorithm for 10 years. It's fine. People stop checking it.
And technical debt.
Old tech has old problems, legacy code, outdated assumptions. Just because it's old doesn't mean it's safe.
In fact, it might mean it's rotting.
Exactly.
The source notes a paradox here. With mature tech, a larger variety of experience data makes risks easier to identify.
But that assumes you are actually looking at the data. If you are complacent, all that data doesn't help you. Maturity breeds false confidence.
Wow. We have really covered some ground here. This Annex B it's exhaustive.
It is, and it needs to be.
Let's synthesize this for the listener. We started with the disclaimer in B.1 context is everything. We look at the complexity of the chaotic world in B.2, the opacity of the black box in B.3.
We looked at the coordination risks of automation in B.4, the danger of the handover.
Then we dove into the raw material of ML in B.5, the data, the poisoning, the drift. We touched the cold, hard physical reality of hardware and cosmic rays in B.6.
We walked the timeline in B.7 from design to the dangers of reuse and decommissioning. And finally, we checked the maturity level in B.8, warning against both the new and the old.
It really paints a picture of risk management that is holistic. You can't just be a coder to do this job. You have to be a physicist, a psychologist, a lawyer, a historian, and a sociologist.
That is the ultimate message of BSEM ISO IEC 23894. The source of the risk could be anywhere. If you are sitting in a room only looking for bugs in the Python code, you are missing 90% of the picture.
You can't fix a risk if you think it's a software bug, but it's actually a cosmic ray hitting your memory chip.
Or if it's a human being getting bored. Or if it's a manager deciding to save money by reusing a Facebook tool for police work.
That reuse point really sticks with me. It fundamentally shifts the blame or the responsibility from the tool to the user.
It raises a provocative final thought. We often worry about the AI breaking or going rogue, but B.7 suggests that one of the biggest risks facing us isn't the AI malfunctioning. It's the AI working exactly as designed but being used by humans for the wrong purpose.
The source of the risk isn't the machine, it's the mismatch.
The risk is in the relationship between the machine and the context, and that is a human problem, not a computer problem.
That is something for everyone listening to chew on. So here is our challenge to you. Look at your own systems. Look at the AI you are building or buying or just using, and ask yourself, which of these B sections is my biggest blind spot?
Are you watching the cosmic rays? Or are you watching the drift? Or are you just watching your own complacency? You need to watch it all.
On that note, thanks for diving deep with us into the granular, physical, sometimes terrifying world of AI risk sources. We'll see you next time.
Stay safe out there.